We're going to be going over radicals, rational exponents, and operations with polynomials. So to start, let's review some of our property of square roots. So the first rule, and this actually applies to all roots, not just square roots, but we'll make it simple with square roots. So product rule for square root says that if you're multiplying two things under a square root, you can split it up. So you can split up those square root signs, and the corollary or the reverse is true, that if you are multiplying square roots, it's okay to combine them under one square root and then simplify. The same is true for division or the quotient rule for square roots. If you have two quantities underneath a square root and you're dividing, you're allowed to split up that square root, or it's kind of like distributive property, but not exactly. Same thing, if you have two square roots, you're allowed to go from two square roots to one square root. In division, now this only works in division and multiplication. It does not work with addition or subtraction, so be aware of that. So in example 1, this does ask us to simplify, so the easiest thing for you to do is to go ahead and multiply those. So 5 times 10 is 50, and x times x is x squared. And then we always simplify our square roots in pre-cal, always simplify our square roots. And so what we're looking for is perfect squares. So I'm going to do this my way. You may have learned the factor tree way. The nice thing about being at this level of math, as long as the math is correct, you can do it your preferred method. Again, the math has to make sense, but so one trick that I like to do, or the way that I like to approach these problems, is I like to find the perfect squares. Since I'm dealing with square roots, I would find any one of these numbers right here. So I'm trying to find it in terms of perfect squares, like 1, 4, 9, 16, 25, 36, 49, and I'm just going to put a dot, 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 because you guys know your perfect squares. And then the reason why I like to do this is because then I draw little square roots on it and I go, what's the square root of 25? Oh, that's 5. And sometimes students have problems remembering which one does the square root go on and which one doesn't. So this one, it's very clear. I can simplify the square root of 25 to 5. I can't simplify the square root of 2. And then as far as x squared goes, just keep this in mind that in math, the square root undoes the square, so that's just x. So you can think of it that way, or you can do your little factor tree and say, because it's a square root, I need 2 of a kind. I have 2 of a kind, so then it would just be x. And then we have that radical 2 left over. So that's the first problem. As you guys are working through these notes, I would strongly encourage you to pause the video and then try the problem and then see if you get the correct answer. And sometimes I'll show you 2 different approaches just because there's a customary way that students progress in these, and then there's the, hey, maybe it's a shortcut or a different way to look at it. So just be aware of that. So with this one, I have 2 radicals, so I'm going to use that property right there, and I'm going to combine it into 1. So 150 divided by 2. And I'll just write this just so that you guys can see on a test. I wouldn't need to see this step. You can go straight to this one, which would just be 75x squared. And again, me breaking it down into my perfect squares and square rooting, and then that would give me 5. And then I still have to square root that x squared, which just undoes the square. So that's x and then root 3. So that's the answer for that one. I do like to box my answers. You don't have to, but it makes it very clear that I'm done simplifying with the problem. So on this part right here, you might have not thought to use this. You might have said, oh no, there's square root in the denominator, so I need to rationalize. So I actually have that problem right here and just showing you we're going to get the exact same answer. So what I was saying was that you might go, okay, there's square root 2x, so I need to multiply or rationalize, which we'll get to in a second. I just want you to be able to follow this problem through. So if you did that, 150 times 2 is 300, and x cubed times x is x to the 4th. And then down here you have square root 2x times square root 2x, which is 4x squared, but I kind of want you to not think about it that way. I'd rather you see it as 2x twice, and that way we can say the square root undoes the square. So much of math is reversing what you've done or undoing what you've done, and to be able to see that procedure happen, it's a good context for you to have at this beginning level of honors pre-cal. Anywho, 300, my perfect square there would be 103, and then I'd square root both of those, so I'd get 10. The x to the fourth, when I square root that, I get x squared, and then I still have a radical 3. And then in the denominator with the square root, undoing the square, I get 2x. And then when I reduce properly, because these are common factors, 10 divided by 2 is 5, and x squared divided by x is x. So you can see we get the same thing we did either way. Moving on. Number 2 asks you to add, so just be really careful when you add. You need the same number under the radical to be able to combine like terms essentially. So what you're always going to do is simplify first. So I'm going to find my perfect square. Again, you're more than welcome to do factor trees. And I get 5, and then the square root of 9 is 3, and since we're multiplying, 5 times 3 is 15, and there's a radical 3 left over, plus, there's my breakdown with my perfect square of 4, so then I'm going to get 2 root 3, and now you can see I have the same number under the radical. That's actually called the radicand. Who knows why, but so what you're going to do with that is I have 15 root 3's, and then I add 2 more root 3's, so I would end up with 17 root 3. And that's your final answer. But again, you can't just go 27 plus 12 is 41. That doesn't work. You have to have the same radicals underneath, much the same way as when you're combining like terms with x's. You can't do 5x and add it to x squared. You need to have the same terms there. Okay, moving on now to our next concept, which is rationalizing. So I'll come up here and use this definition in a second, but I'm going to go right here to this one. So when we rationalize, there's 2 things that you can do. So first is if you just have one term in the denominator. So I'm going to show you the way that I would approach this, and then I do have a alternate way for the way I think students would approach it. So if I have root 12 here, my gut being a math teacher is to go, okay, well this is really 6 all over 2 root 3, because if I factor tree based upon perfect squares and simplify, that's 2 root 3. A rational number means it's not irrational, which means like square root of 3 is an irrational number, but 2 is a rational number. It can be written as a fraction. So the only irrational part of this denominator is the radical 3. So that's what I'm going to multiply top and bottom by. So in the numerator, when I do that multiplication, I get 6 root 3. And in the denominator, though, I'm getting 2 times root 3 times root 3, which means I have root 3 twice, which means root 3 squared. So the square is going to undo the root. So I'm really just going to have 2 times 3, which is 6. And then because these are common factors, factors are products, meaning you needed to multiply 2 things together or divide to get a factor. Don't get that confused with this like right here. 4 and root 5 are terms. Terms are separated by pluses and minuses. I can't just cancel these and reduce these right here. I can only reduce common factors, which means that multiplication had to be happening. Multiplication is not happening in the denominator. We'll get into this problem in a second. But on this problem right here, I can reduce this because 6 times root 3 and just 6, there's no adding or subtracting going on, so it can reduce, and that gives me root 3. So I know students might actually approach it a different way, which is great. I learn a lot from my students because they think of things I don't think of. On this one, this is the most common alternative approach to this problem. So students will multiply both sides by, or numerator and denominator by root 12. They won't simplify first like I did. It's fine. We're going to arrive at the same solution. We're just taking a different journey to get there. So we'll rationalize, great thought, root 12, root 12. In the numerator, 6 times root 12 is 6 root 12, and in the denominator I have that 12 times 12, which is 12 squared, and then I'm square rooting that, so it's going to undo that square, so I'll have 12. Another way to think of it is 12 times 12 is 144. The square root of 144 is 12, so we get it many different ways. Now I need to simplify this because this is a radical that hasn't been simplified, so I do 4 times 3 and then square root. There's already 6 out here, so 6 times the square root of 4, which is 2, so 6 times 2 is 12. Still have the root 3 and then the 12, and then those will reduce because they are common factors. So if you took that approach, you can do it that way as well. Okay, back up here to conjugates. We use conjugates so much. You have to be familiar with conjugates. If you're like, yeah, I kind of know conjugates. Conjugates are great. They make our life so much easier. So we're going to use those a lot. So basically, you need to know your definition of a conjugate. Conjugate deals with terms. If you actually look at this term and this term, the first terms and the second terms, they're exactly the same. The only thing that's different with conjugates is the sign in between them. So if you started with a minus, your conjugate would be a plus. If you started with a plus, your conjugate would be a minus. So the reason why we can't in this problem just multiply top and bottom by radical 5 is because I would actually have to do something like this, and when I go to distribute the radical 5 to the 4, it'd be 4 radical 5, and it wouldn't eliminate the radical in the denominator, which means I didn't complete the directions that say rationalize. So when you start having two terms, you need to use the conjugate. So again, when you do the conjugate, it's going to be 4 and root 5. The terms are the same. The only thing that you're changing is the sign in between. And in math, to keep this equivalent, to keep equivalency, we need to multiply top and bottom by that. Because if you really look at this statement right here, this expression is just 1, but we're manipulating it to be a 1 to our advantage. So we're just going to follow this through at this point now. 8 times 4 is 32, minus 8 root 5. All over 4 times 4, which is 16, minus 4 root 5, plus 4 root 5, minus square root 5 squared, because I have two of them. So here's the beauty of the conjugate. Do you see this right here? Minus 4 root 5 plus 4 root 5. Those are opposites, and so they will cancel out to 0. When you start getting the hang of conjugates, you can just go 4 times 4 is 16, and square root 5 and square root 5 would just be 5. We'll get into that in a second. But you won't even have to multiply by foiling. You'll recognize the pattern and just go from there. So we have 32 minus 8 root 5 all over 16 minus 5, because 16 minus square root 5 squared, that square is undoing that square root, so it's 5. Another way to think of it is just think of 5 times 5 is 25. The square root of 25 is 5. And then, of course, simplifying further, and we get 11. Because 11 does not have anything in common with 32 and 8, we cannot simplify any further. However, you might see some solutions written like this, and you just need to be comfortable. All they're doing in this one right here is writing it as two fractions or two terms instead of one. And sometimes that might be helpful in a problem, more helpful than that. So you just got to be able to think of these solutions or these expressions in different forms and know when to use which form. Moving on, now we're going to talk about product and quotient rules for nth roots. This is what I was saying before. Here I have square roots. The same rules apply to any root, so cubed roots, fourth roots, etc. So we give you a real quick simplify. This is the cube root, which means I need 3 of a kind instead of 2 of a kind. So just to remind you of your perfect cubes, you do want to have these memorized. You don't always get to use a calculator. Usually your tests are part calculator, part not. So your fast math facts, your mental math facts, you want to be strong on. Real easy, just make flashcards. So we get to this right here. So I'm looking for a perfect cube here. So I'm going to do 8 times 5. And then instead of just writing a square root, I'm going to make sure I put that cube root in there. The cube root of 8 is 2. I cannot get 3 of a kind out of 5, so this is my answer. Very important to have that 3 there. Over here on this one, though, most students will approach it with the factor tree, so I'm going to show you that real quick. So I need 3 of a kind. There's one set of 3, so that's x. And then there's two left over. I don't have enough to make a third, so this would be x squared. I like to kind of think of it like this, though. I like to go, this is the same thing as this. So this is using this rule up here that says it's okay to split it up. You need 3 of a kind, so x cubed times x squared is x to the 5th. Well, this cube root undoes that cube, so that's where I'm getting that x from, and I can't undo over here, so I get this right here. So same thing, 2 different ways. Moving on to our rational exponents and how to simplify them. Basically, what you need to know, what this definition is saying, is that whenever you have something like, let's say it's 2 to the 3/5 power, this right here, if I want to write it in exponential notation, or sorry, this is exponential notation. If I want to write it in radical notation, this is the power and this is the root. Really easy to remember because power, people of power, are usually at the top, so the top of the fraction, and roots of a tree are at the bottom of the tree, so there's the root. So at the bottom of the fraction. So I'm going to show you 2 approaches for these problems. This would be a very procedural way of doing this. So I would say, okay, 4 to the 3/2, that's interesting. So what I'm going to do is I'm going to do this as my root. So another way to write this would be the square root of 4, and then everything is raised to the 3rd power. And I didn't show you that up here, so let me go ahead and do that real quick. So again, this would be the 5th root of 2 raised to the 3rd power, or depending on context, you could also do it like this, but for what we're using it as today, it's just easier to write it with the power on the outside. So do you know what the square root of 4 is? You're like, yeah, sure, square root of 4 is 2, and then I have 2 cubed, which is 8. When I do these problems, I don't convert to exponential. I get really good at knowing that this means the square root, so I can do it mentally. What's the square root of 4? Oh, it's 2, and then 2 to the 3rd power, because that's the power that's raised there. Another way to think of it is like this. You should be familiar that anything raised to the 1/2 power is the same thing as taking a square root. So anytime you see that, you can go, oh, property of exponent says if I have power to a power, I just multiply. So these are really the same thing. 1 times 3 is 3, 2 times 1 is 2, but I've just manipulated it. We do so much manipulation for simplification purposes. So I manipulated it. So 4 to the 1/2 is 2, and then 2 cubed is 8. So on something like this with the negative exponent, you just need to remember that when you do negative exponents, you need to write it over 1. Or if it's already in the denominator, then the negative, whatever has the negative exponent moves to the numerator. And so we're going to do this one the shortcut way, and then I'll show you the long way. But can I get 5 of a kind out of 32? That means 5th powers. So that's 2. So this is really equal to 1 over 2, and then I have to square it, so that would be 1/4. If that's too much for you, you can think of it like this. The 5th root of 32 squared, which is 1 over 2 squared, which is our 1/4. So that's all of our P3 notes from our textbook. The last little bit is P4, which is operations with polynomials. So we're just going to hash through that real quick. So first thing, when you add or subtract polynomials, you just combine like terms, but the problem here that I've specifically chosen for notes is just a reminder to you that whenever you have subtraction, you're actually adding the opposite. So I just want to make sure that you distribute to all terms that negative sign. So this first quantity is staying the same, but a negative, so that would be positive 7x cubed minus 2x squared plus 5x and minus 9. And then I'm going to combine like terms. So 13x cubed and 7x cubed is 20x cubed. Negative 9x squared and negative 2x squared is negative 11x squared. Negative 7x and 5x is negative 2x, and 1 minus 9 is negative 8. I'm going to pause right there and just let you know if I make a mistake in a video, please ask me about it the next day. If you just don't understand where something came from, I want you to be clear. I am not perfect. I make mistakes. Mistakes help us grow. So if you can help me and make sure that I'm seeing something, or if I didn't explain something very thoroughly, please let me know and I will attempt to clear you up. And if I make a mistake, please just be polite and let me know, and I will also try and clear that up. For example 7, this is just multiplying, so I'm going to show you guys the box method, which is, some of you have already learned that, but basically because I have two terms here, I'm going to do 5x and negative 2. And this is just a way to organize. Some of you don't need this, but some of you it's just helpful. Like if you're prone to making tiny mistakes, then you should take the time to make sure you don't make them. And that might be me making this box. So, and then this one has 3 terms, so I made 3, and I'm just going to multiply each of these. So 5x and 3x squared is 15x cubed minus 25x squared plus 20x minus 6x squared plus 10x minus 8. And then if there's any like terms like these two, I'm going to make sure to combine them. But I'm not going to leave my answer like that. I'm going to make sure that I pull it out of my tool to a complete mathematical statement. And so there's the answer there. If you didn't want to do it this way using the box method, I don't require it, you could do what I call the clamshell, but it's just a big distributive problem. So you're going to want to make sure to distribute that 5x to all 3 of those terms and the negative 2 to all of those terms, and then make sure you combine like terms. Okay. So you might look at this example 7b and think, oh, what a silly question, 3x minus 2 squared. First thing I'm going to tell, or sorry, it's cubed. First thing I'm going to tell you that this is not 27x cubed minus 8. That does not equal that. So many times students make the mistake of distributing this power. Anytime there's a plus or minus involved, you cannot distribute that power. What this actually means is 3x minus 2 times 3x minus 2 times 3x minus 2. So when I go to do this problem, I'm going to start by taking and multiplying the first 2. So that would be 9x squared and then minus 2x, or sorry, minus 6x and then minus another 6x, which would be 12x plus 4. And then 3x minus 2, and then I have to distribute again. I'm actually going to be checking for this tomorrow to make sure that you multiplied this out. I'm not going to put the answer up here. I think you guys are capable of getting it. But what you're going to hear me say something is really strange, and believe me, it's just all for your benefit. It's really been working out well the past 2 terms. So there are certain mistakes that students make over and over again, and I love Pinterest, so I went on Pinterest to figure out what other teachers are doing to help their students not make these mistakes. So this is a very common mistake in the math world, especially for high schoolers, where they just decide, oh, I'm just going to distribute that 3. You cannot shower the power if there's a plus or minus. So I saw that one teacher put up a sign that said, every time you do this error, a puppy dies. So if you hear me tell you, like as I'm walking through, I'll be like, a puppy died. I'll try not to call you a puppy killer. I know that sounds really terrible, but apparently it has something to do with our brain mechanics and how we tie emotion to something, and it just gives us an extra little pause. So If I say, oh, a puppy died, it's just to help you not continue to make the mistake. And it was amazing, the difference in between classes when I was able to use that reminder, how many times students, like the less mistakes that type of mistake they made. It was just amazing. So that's my weird little thing. You'll notice I have tons of weird little things as we progress in the class, but it's all for your benefit and to help you be successful and to be better math students. So that is all for today. See you tomorrow.